for your attendance. Okay. For today, as discussed to you the week prior to last week, what we're going to do is we're going to have feedbacking on the two recordings shared to you. So actually, they are the last two. They are the shall I say the second to the last set of topics that will be discussed in differential equations for module 2, which is first order differential equations. After that, we're going to jump to module 3, which will be now concentrating on the application of first order differential equations. So I hope that you have accessed the links that I placed on Canvas last week as early as Monday morning. And you have already worked out the problems in the problem sets that could be solved using the techniques that you already learned. Okay, so for today, just as a short review, I will go back to those slides just as a review, and then you're going to ask me concerns that you may have regarding those slides. Then we will solve problems concerning the application of the two types of first order differential equations. So now we'll be concentrating on linear and Bernoulli equations. So they are actually first order differential equations. Okay, so let me share my screen. Let me just check. Okay, so this is first order DE. So let me share my screen. Okay, excuse me. So this is first order differential equations, specifically linear differential equations. So this particular type of first order differential equation has to be tested, or actually it's not tested, but has to be compared only in terms of the form. What is the standard form of a linear DE? And if our given differential equation conforms to that form, then we say it is linear. So let me proceed to the next slide. So a linear first order differential equation is written in this form, wherein you have the derivative, and then you have the expression of your unknown function times the p of x expression. P of x meaning it's a function of x, the independent variable. On the right side, what you have is the q of x. Now, for first order linear differential equations, you need to determine what we call the integrating factor. In most of the textbooks, it's represented as phi, the symbol phi. And how do we determine the integrating factor? You have to first and foremost be able to identify, based on the form of your linear first order differential equation, what is your p of x. Okay, so you have to know what's your p of x. And once you have know already the p of x, you simply make it as the argument of the exponential function which should be integrated. Now, after that, after your evaluation, you are to evaluate this phi. And the formula in finding the solution of your first order differential equation would be this. The left side of that formula is the product of the phi, which you have evaluated, times the unknown function. And the right side would be your q of x times the phi, which you will have to, of course, find the integral of. So q of x is taken from here. So your q of x is taken from here, and you're going to multiply it to the predetermined phi. So this is your phi. Okay. Now, let me clear my drawings. If you go to the next slide, you will have an example of a linear first order differential equation. So if you look closely here, it's not yet conforming to the form dy dx equal plus p of x y equal to q of x. It's not yet like that because you have this. So what's done is you divided the entire DE that you have here by x and came up with this expression. Now, having this particular expression, now you can see that your P of x is 1 over x, this one, because the y here is being multiplied to the P of x. And your Q of x is the rest of the expression that is written here on the right side of your DE. So your step 2 is you are to determine the integrating factor wherein the identified P of x you will make as the argument of the exponential function which you need to integrate. So you integrate 1 over x, your P of x, and then make it as the exponent of the e. So integrating 1 over x dx is ln of x, and as discussed in your EMA 101, whenever you see an e raised to an ln, that's actually equivalent to 1. So what is left here is simply x. So if you're going to apply the formula for your linear first order differential equation, which says that your unknown function y, so that's your y, is to be multiplied by the integrating factor phi, and that's the x that you're seeing here. So we're simply following the formula. And then this one, the right side should be evaluated. So your right side, actually, your right side is negative 4 over x. And it is to be, so I'll write here negative 4 over x for the Q of x. And it is to be multiplied by the phi, which is the x. And you are to integrate it. So of course, the x will cancel each other, leaving you with a negative 4 to integrate. When you integrate negative 4 dx, that will give you a negative 4x. That is why you see here a positive 4x on the left. So you have the c, the arbitrary constant of integration c on the right side. Okay? Any questions so far as to this particular example for our first order differential equation?
So those are the difference between the two, the point.
Okay, there's none. So I will clear my markings here and let's proceed to the next slide. Oh, I only have one example here. Oh. Okay, so I'll give you another example. Let me go to let me stop sharing for now. I'll go to the board and give you another example for linear D.
In the first week of the lesson. But others wrote the Philippine peso sign, the peso sign, after the amount. Okay, they do this.
Okay, so this is our board now. And I'll give you the second example here. Maybe I'm miswriting it there or I have accidentally deleted it. So I'll give you a new example for linear first order differential equations. So let's say, for example, you're given
the value of the amount. So this one is the way. Okay. So this is the proper way of that using the peso. I mean the peso sign. It should be written before, not
Okay, I intentionally selected this particular DA because it doesn't look simple. And at first glance, of course, it doesn't look linear. So you have to make it linear. So if it has to look linear, class, it's important that you isolate the derivative. You isolate the given derivative in your differential equation. And doing that, before you can do that, let's check whether we can simplify what we have here on the right side. So you could see that you have a sine x here and another sine x here on the second term. So that could be factored out. So you will have here sine x times you have the sine of x times 1 plus cosine of x minus y. Okay. Now, I simply factored out, let me change the color of my font. I simply factored out the sign of x in here, the common one, and this is the corresponding factored sign of x. It's to be multiplied by, for this one you have 1, and for this one you have cosine of x, and you have the y. Okay, now let me go back to what is written here on the left side. So I have 1 plus the cosine of x times y prime. Now I will, as I said, we need to isolate the y prime here. So we will divide our entire differential equation by the quantity 1 plus cosine of x. That will eliminate this one in here, giving you a y prime being equal to, now class, if you're going to distribute the 1 plus cosine of x to these two terms that we have, what is left here is the sine of x. The sine of x multiplied to this sine of x will be sine squared x. This one is gone after you have done already the division. Whereas in here, I will have a minus. If the sine of x is distributed to the y, I will have something like this. Minus sine of x over 1 plus the cosine of x times y. I hope you follow. You need to distribute this as a divisor to the expanded form of what is written here on the right side of your equation. And this is that particular simplified form of the expanded form of the right side divided by 1 plus the cosine of x. Still, this does not look like a first order linear differential equation because I only have the derivative on the left. A first order linear differential equation should have the derivative. If I transfer this on the left, I will have plus sine of x over 1 plus the cosine of x times y. And this one is left on the right side, which is your sine squared of x. If you look at it very intently, this is now your p of x. This entire expression is your p of x based on the form. And this function of x expression on the right side of your equation is your q of x. So now, from the original not so linear form of the differential equation, you have converted it to linear. So there are a lot of differential equations, first order differential equations that are actually linear, but they don't look like that at first. So you have to make them conform to the form of a first order linear differential equations. Okay, so I haven't already written your DE, you're given DE in the linear form, then the next step, of course, is to determine the integrating factor. So you go to the next page. That integrating factor is actually the phi, which is e raised to the p of x dx. So what we're going to do, you're going to pick out the p of x here. So this is your p of x, this entire expression. So you have the sine of x over 1 plus the cosine of x dx. Okay? Now to finish this one, all you have to recall is your integral calculus. If we set the entire expression here as your u, the numerator should be checked whether it's the du. So if this is your u, your du actually is negative sine x dx. So this should be negative. If that is the case, I will have something like this. My answer is e raised to negative ln of 1 plus the cosine of x. Why ln? Because you have du over u. So ln of 1 plus cosine x, and you have negative here. Now, what is this negative? It's like, if you're going to write this, it's like 1 plus the cosine of x raised to negative 1 from your EMMA 101 then, your differential calculus. The coefficient or the number that is written before your ln is actually the exponent of the argument of such an ln. Why would Why would I write it like this? It's because I want to have this one.
You don't have.
Because just like in example number 1, this one is equivalent to 1. So that tells us,
You will get it back. Okay.
that your phi is actually 1 plus cosine of x raised to negative 1. So you have this negative 1, meaning it's 1 over 1 plus the cosine of x. Okay, now with that phi, you now can write the solution of your first order linear DE. So the formula is y times the phi times the integral of q of x times the phi dx. Now your y, what is your phi? This is our phi here. 1. Okay, so this is your phi. Your q of x, you go back and determine the q of x. So actually our q of x is this one, sine squared of x. So I'll place here sine squared of x times 1 over 1 plus cosine of x, right? This is your phi, your 1 plus cosine of x dx. So again, you have another integral challenge in here. Okay? How will you find the integral of this expression? You get the corresponding equivalent identity of the sine squared. And that's 1 minus cosine squared of x. Then copy this one, 1 plus cosine of x. Okay? Now, this one can be expanded, again, using your trigonometric identity. So, it could be expanded to what? You have 1 minus cosine of x and 1 plus cosine of x. And you have 1 plus cosine of x here. And you have here dx. So, what happens here? You can cancel the expression 1 plus cosine of x, leaving you with a very simple integral to process on the right side. So let's go to our next slide. Your left side, your left side, which is y over 1 plus cosine of x, is equated to then, it's like this one. Now it's left with this integral only. So you will have 1 minus cosine x dx. So if you integrate this, I think it's very simple already. So you will have an x for the first term, and the integral of the cosine is positive sine. Okay, last C. So if you want to write your solution in explicit form, you may cross multiply this 1 plus cosine of x expression on the right side. So you have y equal to 1 plus the cosine of x, and that's it. Then you will have x minus sine x plus c. Okay, so this is now the solution of your linear first order differential equations. So it looked not so linear originally as given, but after subsequent simplification, it was made to look linear. Then once you have made it look linear, you identify the P of X and the Q of X because it's important in following the formula that you will later on process. So if you have the P of X already determined, this is it. We just introduce the negative sign here so that we can have an ln. This negative 1 was placed in here. That way we can have e raised to an ln, which is 1, giving us a phi, which is 1 plus the cosine of x. And then we just follow the formula. Your unknown function times the phi on the left side should be equated to the product of the q of x, which is actually the sine squared of x here, and the phi again. So actually, in just one example, you did a lot of recall of the previous techniques and principles learned in mathematics. You recalled identities, you recalled algebra, you recalled integral calculus, because you can never finish the solution of this DE without your calculus. You cannot also process this integral without the use of the identity equivalent of the sine squared of x. So I will hold you responsible to review on those things because they're supposed to be learned already in your previous course. So then we just process the integral and this is our answer. Okay? Now, any question as to the second example that I gave? Any question? Okay, so
Miss,
next,
excuse, miss. Paano
yeah.
ma-identify, miss, ang Q of X, miss?
Ang Q of X is the expression on the right side of your DE. It should be a function of X only. So you see this one, the sine squared of X is the remaining X expression here on the right side. So that's it. This is your Q of X. In terms of form, I'd like to go back to our slide because probably you haven't. Okay, in the slide, this is it. Your linear DE should have this form. You have the derivative, you have the unknown function times the P of X. The right side, note, it should solely be an expression of X, and that's your Q of X. And this is your Q of X. So in terms of the example that we have processed a while ago, the expression on the right side is your Q of X. Okay, your P of X is the expression that is being multiplied to Y on the left side of your D. So the requisite or the requirement for your first order differential equation to be linear is you should have these three. You have the derivative, you have this P of X times Y, your unknown function expression, and you have the Q of X on the right side. If it does not conform to this form, class, don't solve it using linear technique because that would give you a wrong, of course, solution, a wrong answer for your differential equation.
Bali, fix na miss, nga formula, miss, no?
Yes, this is a fixed formula.
Okay, miss. Thank you.
Actually, this is not the formula. This is the form of the first order linear differential equation. So it's a fixed form, and you just have to recall this procedure. Find the integrating factor and process it using this particular formula. Okay, I have the chart here. Lateness, it's okay. Okay, any more question?
Miss, excuse me.
Yes.
Paano, Miss, mabalaan, Miss, kung linear or non-linear ang DA, Miss?
You have to make it conform to this form. The form should be like this for it to be linear. If it's not like this in form, it's not linear. Excuse, excuse for a while,
Okay,
class.
thank you.
Okay. So there's no test class for first order linear differential equation, you only need to check whether the given differential equation, if not really originally given in this form, could be rendered in this form, or meaning, in other ways, saying it could make look like this one. If it's not going to look like this, it's not a linear first order DE. So amo to kayo na ginhambal ko, suliton ko. It should have the derivative, no coefficient on it. It should have the product of your unknown function and an expression in terms of the independent variable. So these two should be found on the left side of the DE. And what is written on the right side is simply the Q of X. Now question, what if the expression in terms of X on the right side has, let's say, a Y or a Y raised to 2, a Y raised to 3? Does that not make it linear? So don't solve it using the procedure that was discussed to you. It should be solved in a different manner. Okay? Any question? Some more questions? Okay, so I will stop sharing on this slide and I'll go to the Bernoulli equation slide. Let me check. Okay, let me share a new one.
Okay, now for those who
I always discuss these two parallel lessons. It's because in terms of form class, they look really very similar. Okay, as for the, this is still linear, sorry. It's the other, it should be the other one. We'll have the Bernoulli's equation now. Okay. Now, for Bernoulli's equation, I'd like you to look very closely. Can anybody in the class tell me how is it similar to linear and how is it not similar to linear? What makes it similar to linear and what makes it not similar to linear?
Bernoulli has a degrees on its cube X.
Okay, the only difference, actually there's only one difference in Bernoulli of Bernoulli's equation to your linear differential equation. And let me annotate. Sorry. Now you have this one. This is the primary difference between the two. This. Your linear DE does not have the y raised to n. So however, if you see this form in your first order DE, the requirement is that n should not be equal to 0 and 1. So it should be other than this. It could be a fraction. It could even be negative class as long as it's not 0 and it's not equal to 1. Then it's a Bernoulli equation. If it's a Bernoulli equation, processing it is actually very similar or comparable to that of linear. The difference in determining the integrating factor for a Bernoulli's equation is this one. Okay, that's the only difference. You identify what this n is, and your integral, which is p of x dx, should have a constant written before it, which is 1 minus n. Amulan din na siyang kinalainila. The formula in finding the integrating factor will have 1 minus n. Now, your step 2 is, of course, the formula already. Okay? Miss Dinah, Juliana, it's not Miss Hannah. Sorry about that, class. So now your formula will be this. So the only difference about the formula for linear is this. Okay, and you have this. Formula for the integrating factor has 1 minus n. in the integral of p of x dx. Formula for determining the solution of your Bernoulli's equation has already 1 minus n to your y. So in your linear D, this is just simply y phi, product of the y and the phi. Now you have y raised to 1 minus n times the phi. And on the right side, you have 1 minus n times the integral of q of x and phi product in here. So in your linear, you don't have this 1 minus n. So that's the only difference. The challenge always, class, that I see for students in determining the solution of a particular, let's say, linear or Bernoulli's equation is, first and foremost, you have to make sure that your given differential equation is linear or Bernoulli. So if it's not linear, if it's not Bernoulli, it should not be solved using the steps in here that is indicated. Okay, now, I think since you have already listened to this, I will not discuss this anymore. And this is the example. Never will you think that this one is Bernoulli's equation, right? Because is not written in Bernoulli equation form. But notice how was it made Bernoulli. So there was the division of your dy by dx. And how was it done in this case? So let me annotate. I'm sorry again, class. That's my daughter asking for something. So in order for this one to be rendered as a Bernoulli equation, you divide it by dx. So the question maybe that will come in mind, why divide it by dx? That way you will have the presence of a derivative. And if you're going to divide it by dx, it is a requirement in both linear and Bernoulli's equation that you isolate your derivative. So if you have a derivative of dy dx, this should be eliminated as a coefficient of your differential of y. So you're going to divide by 2x. Now, if you're going to divide by 2x dx, this should be the resulting expression after that. So this is your algebra already. Your expanded form for this one, 6y cubed minus xy minus y, that's the expanded form already of this one. You need to divide by 2x because you're going to divide the entire equation by 2x. If you divide this one by 2x, that eliminates the 2x already. And if you divide this one by dx, that will also eliminate dx, introducing 2x. So this is already your DE after that. After you have divided the original differential equation by 2x dx. Okay, so this is your DE. Now, after that, it's very important that you again isolate a portion of this rational expression that you have that contains the what? The y and an expression in terms of the x, and that would be constituting your p of xy. Now, you may be asking, how is it done, Miss Ali? So, in this case, class, you see this? This one is y cube. So, hindi ni siya pwede ni mo nga imuon nga p of xy because your y is already raised to 3. So what should come into your mind is that your p of xy should be coming from this one. So I'll write it here. Then I will have a negative. If I factor out the y, so that should be the y, it should be multiplied to x for this one. And this, since this one is negative, so I should have plus 1. Notice that if I expand this one, negative yx minus y, it's still the same as this. And you will divide this by 2x. And I will have this one, let's say plus your dy dx. So I'm trying to make it look similar to Bernoulli equation. This one should remain on the right side, and it should be 6 over 2x. You have 6 divided by 2x and this y cube here. Okay? So I will have something like this. This is now the form of your Bernoulli's equation after I have written it in here. Okay, where this one came from is actually from this one. So you have dy dx minus, so you have x plus 1 over 2x times y, and it should be equated to, if you process this should be 3. So negative, wait class. So if this is negative, and this one is transferred to the right, that should be negative. So this should be negative. I'm miswriting the negative because this one is on the left. You transfer it on the right. So you have negative 3 over x times y cubed. Now, the process of getting the integrating factor is similar to that of linear DE, only that you introduce this one. Okay? And you have n here, by the way, is equal to 3. Okay? So you have here a 3 for the n. Where did you get that, Miss Ali, in here? And so you have e raised to 1 minus 3. So that would be negative 2. Your p of x plus is this entire expression. Don't forget that you should have a negative. So this should be included. If you miss to write the negative in your class, your integrating factor will be very wrong because it's very important that you affix the negative sign. So if you have this one now, based on what you have learned in processing rational expression, you need to first do division or rules of exponents, that is. So we can cancel the 2 here, and this one would be already positive, but it would be like this, class e raised to the integral of x plus 1 over x dx, and I'll write it here again. So it would be e raised to the integral of 1 plus 1 over x dx. So x over x is 1 and dx is multiplied to also to 1 over x in the second term. If you're going to process this integral, class, this would be e raised to, for this, that would be x, plus this, that would be ln of x. If you use the rules of exponents, if you're adding, if you have added exponents, it's like 2e's which you are multiplying. This one could be simplified as 1 again, and that would be x. So your phi, your final phi for this Bernoulli equation is actually x coming from here multiplied to e raised to x. Okay? Now, if I'm going to clear my markings here and proceed to the next slide. So you have this one already. Your formula for the solution of a Bernoulli equation. So it's y raised to negative 2. This is your phi. And you have 1 minus 3. That would be negative 2. And you have here your q of x. Your q of x is the negative 3 over x. Let me go back to that so you will recall what is your q of x. Oh, sorry. Your q of x is this one based on the way we have written it as Bernoulli equation. So your q of x has to be multiplied to the phi, just like this one in here, leaving you with a negative 3e raised to x. So negative 3 times negative 2, that would be a 6, and you will leave and you will just have the e raised to x to be integrated. So e raised to x will have an integral of e raised to x. So this is now your solution. If you want it simplified, since this one is y raised to negative 2, and that would be equivalent to 1 over y squared. So you see that you have y squared already appearing here, because it's like this one is x e raised to x over y squared. So you do cross multiplication, and this is already the final solution of your Bernoulli's equation. Okay, now do you have any questions so far as to what I have discussed here before I find another example for you?
Miss, excuse me. Ang
Yes.
x e raised to x, miss, di ba? Phi na, miss, no?
This is your fee.
Okay, miss. Thank you.
So this actually, let me just your formula for your Bernoulli equation. Where is it? It's this. So the only thing that makes it different than your linear differential equation is this one. Wala ni sa linear, wala man ni sa linear. Okay? In determining the integrating factor, amo man lang ni ang wala sa linear. The rest the same. In terms of form, what is not in the linear form is this one. Okay? So y, the n rather in your y written on the right side could be any number. Any. It could be a decimal, it could be negative, it could be a fraction, it could be a whole number, as long as it's a 0 and or 1. Because it will not be Bernoulli equation anymore if your n is equal to 0. If your n is equal to 0, this one would be linear, because anything raised to 0 is 1. So this will be converted into linear first order DE in form. If n is equal to 1, this is separable. Why? You just have to transfer the p of x on the other side and then factor out the y. That makes it separable already. Your y should go with the dy by division. Your dx should be transferred here to your p of x and q of x, which you have combined. Okay, so amo na nga hindi dapat ang n in here, it should not be 0 or 1. Otherwise, it's not, in terms of form, Bernoulli equation. Okay, some more questions? Let me check. So no question in the chat box. I still have 10 minutes, so better make use of it. Any question? Any question? Let me pick an example here for you. Okay, let me clear my drawings in here and let us process a new Bernoulli equation. Okay. So this is your second example. Wait, class, I'm not sure whether this one has another example. Okay, so I only gave one, so I will give you another one. So this is the second example for Bernoulli equation. And you have 2x cubed y prime. And you have y times y squared plus 3x squared. Okay, that's it. If you look at it, it's really not Bernoulli equation. Okay, looking at it, it's not Bernoulli equation. So we'll try to make it Bernoulli. You do expansion first. So let's see, it will be y cubed plus 3x squared y Right? So the y cube here alone might make you think that this has already been Bernoulli in a sense because my y is raised to an exponent other than 1 and 0. And probably, I'm not yet sure, we're not yet sure if you're doing this, that this would be your p of xy. So the next thing that we will do is we will isolate your y prime in here on the left side of your dE. Isolate it, that way you will have simply the derivative of your unknown function. How do we do that? So we divide by 2x cubed. So the entire dE will be divided by 2x cubed. That leaves you with a y prime here on the left. And notice that on the right side, if I will distribute this one, I will have something like this. 3x squared over 2x cubed. I'll isolate the y as if I'm multiplying these two, and I will have this plus 1 over 2x cubed y cubed. See that? Now, it still doesn't look like Bernoulli, so we will simplify. So if we will simplify, we get this one, x squared. That leaves us with one more here. And the resulting expression, this one, we can't do anything about it anymore. So you will have something like in here, you will have a class half 3x squared. Okay, so you will have something like 3 over 2x for this one times y, and you will have here 1 over 2x cubed y cubed. Now I will make it look Bernoulli by transferring this one on the left side of the equation. So you will have y prime. Since I'm transferring, that will be minus because this one is positive in here. So 3 over 2x times y, and it should be equated to, my right side should, sorry. So my right side should be this one, the 2x cubed, or that would be y cubed times 1 over 2x cubed. Now, if you look at this very closely, class, this one is your p of x. This one is your q of x. Right? Now, then the next would be determining the integrating factor. So if we will determine the integrating factor for a Bernoulli equation, that is equal to e raised to. By the way, your n here is equal to 3. So that would be the integral of 1 minus 3. So that would be negative 2. And this should be your p of x, minus 3 over 2x dx. So I get to cancel the 2's, leaving me with a 3 over x. So this is actually e raised to the integral, this time positive already. So 3, I'll place it outside the integral sign, dx over x. This is equal to e raised to 3 ln of x, which is equal to e raised to the ln of x cubed. This one being equal to 1, so this is equal to x cubed. So that's your phi already. So in terms of the formula for a Bernoulli equation, that should be y raised to 1 minus n. Our n is 3. Then your phi is x cubed. And it should be equated to an integral here, which is 3 multiplied to a 1 minus n also. Then you check what is your q of x. Your q of x here is this one, okay? 1 over 2x cubed. So you will have here 1 over 2x cubed. Be careful to check the signs. I do also miss it at times. So it's positive, so then it would be positive here. Times the phi. What is our phi? That is x cubed dx. So you have on the left side now, this is actually y raised to negative 2. So it could be written then as x cubed over y squared. While this one is -2, this one is -2, that cancels with this. And this one cancels with this, leaving us with the negative of the integral of dx. So -2 is cancelled with this 2. Your x cube is cancelled with the x cube of the phi. So there's no function of x expression here except a constant, which is -1, coming from the -2 in here. So you have x cubed over y squared equal to -x plus c. Again, if you want to simplify, this is x cubed being equal to -x plus c times, or I can place it here, y squared, or write it properly. The x is negative, so we'll write it here like this. We will have y squared times c minus x. Okay? So this is the solution of this particular Bernoulli equation. A question might be like, how do we know means that it's Bernoulli, that it's linear, that it's separable, that it's homogeneous, that it's exact, and we still have 2 more things to discuss. You will learn as you go along. So you have to test first in terms of form, whether the form that is given to you is comparable to a particular type. If it's not comparable to a particular type of first order DE, then check whether it can be made to look like that particular type. If not, don't hindi pagpiliton nga maamugi na siya kung hindi siya amo na. And maybe it could be solved by a different manner or by a different technique. Now, so far as what we have discussed, there are only 2 types which you need to do the test. The homogeneity test for homogeneous DE and the exactness test for exact DE. The others, the separable, the linear, and the Bernoulli, have to conform to a particular form of first order differential equation. If it will not conform to that, then don't insist that it should be solved like that. Maybe it will fall on the last 2 topics that I will be discussing. Now, 1 minute. Do you have any question? Okay, no question. I will stop sharing if there's none. So what will happen, class, on Wednesday? Let me just did you all write your name here on the attendance in the chat box? So please make sure that your name is written here because I'm really checking attendance, okay? Though I haven't yet done it specifically and presented to you the checking of the attendance as to who was able to be present 100% of the time or who was able to incur absences. But I will do so once my time permits me to do so, okay? Okay. Okay, any questions, class? And